Today I'm going to be talking about the long-term effects of claying on non-wetting soils and plant nutrition. And I suppose when you start talking about non-wetting soils, I feel almost like I'm the warm-up person for Steve Davies. So I'll probably try and set the scene a little bit here, and I'll specifically be talking about claying and also plant nutrition on these non-wetting soils. Just really want to acknowledge Richard Bell and also Stan Sochacki from Murdoch University, who are part of the More Profit from Plant Nutrition program within GRDC, and also Steve Davies, who's been instrumental in helping us with this work. So the topics I want to cover are really the properties of water repellent sands. There's probably a little bit of background setting the scene, the effects of clay on water repellents, and the long-term claying and ripping trial results which we have on the south coast, and then going into some of the aspects of claying and also crop nutrition. I think most of you are probably aware of water repellents. It's really a factor which we see in our sandy soils. It's related to waxes and also long-chain fatty acids which coat the sand particles and render them hydrophobic or water repellent. If you start looking at the areas which are most prone, we see it's virtually the sandplain areas on the south coast and also in the north part of the state. But we've also got areas throughout the state which have a high probability of having water repellent soils. If we start looking at a profile with a high level of water repellents, and I've just got here 0 to 15 centimetres depth, 15 to 40 and 40 plus. The MED value is the molarity of ethanol droplet test, and it tells us how water repellent these soils are. And anything above 2.5 is just highly repellent. So you can see in this profile, and it's very common in a lot of water repellent profiles, that we've got in the top 15 centimetres, in that organically stained layer, it can be highly water repellent, but in the sand layer below that, it's not repellent at all. And then once you get into the clays, they're not repellent either. So really the issue is in that top 15 to 20 centimetres that we have the problem. The other thing in these soils is that they can have multiple constraints. Yep, okay. Okay. So in these soils, we've got water repellents. We've also got pH issues. You can see normally we go from a pH of about 5-ish. It decreases as we get into this bleached layer. Lower organic carbon as it progresses down the profile. And also we tend to find that the clay levels in these profiles are very low too, probably about 1% at the surface. And as a consequence of the low clay and also low organic carbon levels in these soils, we've also got low nutrient retention. And we measure the nutrient retention by the cation exchange capacity. So we're down about 4 here, but once we get into the clays, it comes up to about 9 or 10, which is double what we see in the top soils. I suppose over the last few years we've been very fortunate to have a great deal of research which has been done on water repellent soils. Margaret Rope has been doing a lot of work on on-row seeding, using those root channels to try and channel water deeper down into the profile. Clay delving is being used to bring up clay, particularly where it's within about 50 or 60 centimetres of the surface. There's some claying and spading work which is currently being done, and also the work which Steve's probably been most involved with the moldboard ploughing or profile inversion. What I want to do is just talk about claying. And this is a clay pit on a commercial property at Condingup, and here the clay is being extracted from obviously below the ground and then just transported around the paddock. The clay is highly sodic, so it disperses over the sand particles, rendering the soil wettable. The key concern is that it's highly costly. To do this sort of operation, you're looking at somewhere between $500 and $800 per hectare. So if a farmer is going to sort of clay their paddocks, they want to have confidence that they're going to have long-term results, that it's profitable, and that it's not going to be a seasonal effect. It's going to be virtually every season they're getting a a true return from that claying operation. So what is the effect of clay on wetting? Once again, we've got this MED value here, which is a measure of water repellence, 3 being highly repellent, and then clay values here ranging from 2% up to 14%. Generally, as the clay increases, the wettability of the soil increases, water repellence decreases, and we can see that. But what we've found on the south coast is that the higher the organic carbon content of the soil, the more clay we need in the profile to actually overcome that water repellence issue. And so to get down to 0.5 on a 1% organic carbon soil, we probably need about 2 to 3% clay. To get on a 1.5% organic carbon soil, we probably need up to about 6% clay. We also know that some of the soils around Narrogin, which are probably about having 19% clay, can also be highly water repellent, given that they have very high organic carbon levels. So you can imagine that there's a series of curves, sort of running through here, depending on the carbon levels of the soils. I just want to go through now a long-term experiment which we've run at Davies, which is 50 k's west of Esperance. It was originally set up by Bill Crabtree at Wanfa, but we took it over in about 2004. And the original treatments were 5 clay rates: 0, 50, 100, 200 and 300 tonnes per hectare of clay at 2 depths, just in incorporation depths. I think it was about 8 and 15 centimetres. In subsequent years, we turned those incorporation depths into ripping, plus or minus ripping, to 40 centimetres. The one thing which I do want to mention here is that traditionally we talk about clay rates in tonnes per hectare. I really want people to acknowledge that we're also talking about it in terms of the percentage of clay in the profile that we want to achieve. In these daily up soils, they're probably about 1% organic carbon. Our 300 tonne per hectare clay rate achieved a 7% clay percentage in the topsoil, compared to the clay, our 0 or our control, which is just less than 1% clay. And as you can see from the results in emergence, they really are had quite a profound effect. The trial was set up in a randomised block with 3 reps. I just really want to go through what the long-term effects of this trial were, beginning in 1999 through to 2014. And if there are any missing years, it's because there were funding gaps or it was in pasture. The first thing to notice is that we go from 0 tonnes per hectare of clay up to 300, and you can just see in virtually every year there is a step up in production. And I've got it in terms of percent yield increase over the control. So the control will always be 100%. In last year, we were probably looking at about 0.7 tonne per hectare yield increase over the control. A couple of things here. The first thing is that we got a response virtually in every year to the high rates of clay, beginning immediately after the clay was applied, running up to 2014. We're also seeing that the increase in production due to claying is consistent over time. No matter which sort of year or season, we're still seeing a benefit from the claying. In 2007, for instance, where we got sort of a huge increase in clay, in some years, some of that increase is due to just improvements in crop emergence, as you saw in that previous photo. But in 2007, where we had a pretty good start to the season, we had no differences in crop emergence. And so we're sort of seeing the claying effect having a benefit on cropping beyond just improving emergence in these soils. And I suppose the rest of this talk is starting to look at teasing out, well, what has changed in this profile which is giving us these long-term benefits over time. So we've got our clay rates. going from 0 to 300 tonnes per hectare, clay percentage from 0.8 to 6.6%. What we found was that there was a significant increase in the pH, probably by only about half a unit, but we're still seeing that the clay, which has a pH of about 6 to 7, is still sufficient to be able to bring up the clay, bring up the surface pH of the soil by about half a unit. We also saw that there was an increase in organic carbon percentage over time from 0.9 to 1.1%. Now, in reality, that's not a huge amount. It is highly significant, but it does equate to about 3 tonnes of carbon sequestered in the profile over a 7-year period, or over the period of the project. If we were looking at carbon credits, that could be quite a substantial return to the grower in terms of offsetting the cost of the claying program. And then when we start looking at the nutrition, we saw quite a large increase in phosphate in the profile, and we didn't change the phosphate sort of applications between the treatments. In terms of P, we suspect that this is because the clay was actually holding on to the phosphate in the profile, so we're getting over time greater storage, greater retention in the profile. When we start looking at potassium, however, it's more due to that the clay itself has had about 300 parts per million of potassium in the clay itself, and so we're actually adding potassium to the soil during the claying application. So when we start looking at these values of P and K, these values are highly deficient. 17 parts per million is woeful, and it's not only until we get up to about 200 to 300 parts per million, 200 to 300 tonnes of clay that we start getting into the realms of sufficiency in these soils. The other thing was that we were also seeing increases in sulphur. Once again, that's probably due to sulphur in the clay itself being applied to the soil. So really we're seeing benefits which go beyond just overcoming the non-wetting in these profiles. And finally, when we start looking at the cation exchange capacity, once again nutrient retention, we've increased the nutrient retention in these soils by about 1/3. So highly significant and highly relevant to these soils, where we tend to find that nutrients just flow through the sands pretty quickly. Now, how does this add up for other sites around the state? So some of the work which Richard Bell and Stan Sochacki have been doing is actually measuring the nutrient levels in crops. We've been doing it at Esperance at 2 sites, one at the Dalyup site and also at Gibson, and then Badgingarra and Bulgart. The responses to clay in most of these sites have been highly significant, but the key thing which we're seeing in terms of nutrient effects across the board is just these increases, and this is folia, of K and P within the tissue test, virtually at all the sites. At Bulgart it was just K, but virtually every other site it's both P and K. The values in brackets are actually where we had a decline in nutrient levels, but most of them were still greater than the thresholds for deficiency. So it seems to be a response which is not just limited to one trial site at Dalyup, but across a range of trial sites in the WA wheat belt. So just recouping on this, these are the responses which we got relative to the controls when we start adding it up over each of the years, clay rate versus crop yield increase. And you can see from this our controls at 100%. We really didn't get much benefit from clay rates up to 100 tonnes. And I think at 100 tonnes we were well and truly less than that 3% clay level required to overcome non-wetting. It was still significant, but not nearly enough. Once we get above that 3% at the 200 and 300 tonnes, we started getting up to about 50% yield increases, 40 at the 200 and 53% yield increases for the 300 tonnes of clay. However, even at this site, we were still below the yield potential. Our yield potential should have been almost double what our controls were getting. And that started making us think, well, what other limitation is happening in this soil that we haven't overcome? And some years things just stick out. And when you start seeing a coaxial cable running through a paddock, it's green and the rest of the paddock isn't, you start thinking, well, perhaps the roots just aren't getting down deeper in these soils. That's a coaxial cable. It was put into a 1 metre. And at the same time I took this photo, which was towards the end of the season, I also took a penetrometer reading just to see, well, is it purely due to reduced penetration? We've got depth down here down to 700 millimetres, and then penetration resistance in kilopascals. And you can see here that really over the telecom cable, we were still around about that 2,000 kilopascals, which is ideal for root penetration. However, in the controls, we're almost getting up to about 6,000, which is well and truly beyond what any root system can actually penetrate through. So that gave us a bit of a hint that something was happening. Sometimes it takes a bit of a... putting a penetrometer over a coaxial cable is a pretty risky thing. You're putting a point over a cable. I tell you what, when I got back to the office, the first thing I did was to get onto the internet to make sure it was still working, and fortunately it was. What we found here was that after we ripped in the first year, we got quite good breakout across the site, and also quite good reduction in soil strength down to about 300 or 30 centimetres. Below 30 centimetres, even though we ripped to 40 centimetres, we still couldn't get that bottom 10 to really break out. However, that was after the first year. After the second year, you can see that it virtually collapses in the top 20 centimetres or so. And so the longevity of the ripping is not all that long. And when you start looking at the long-term effect of ripping on this particular site, yes, we did get quite a good response in the first probably 3 years, 20%, and that was additive on top of the claying. But really, for 6 to 8 years afterwards, we're seeing no response from that ripping whatsoever. Okay, how long? A couple of minutes? Okay. I'll just probably go through our clay pit survey. Because we're interested in the properties of the clays and how they affect the soil chemistry, we did a clay pit survey across the south coast in 82 sites, just to see what farmers were bringing up. And these are sites where the farmers have actually used the clay for amending their non-wetting. First thing is that there's a huge range of clay, from about 40% up to 50%, up to 75%. At 75%, you've got a potential issue in that if you're applying that at very high rates, you're likely to start, and you can't incorporate it well, then you're going to be creating a brick-like structure. And this is why I always go back to what percentage clay we really need to have in these soils to overcome the non-wetting. Benefits from pH, and I've got nutrient benefits, potential issues, and nutrient limitations. As I've mentioned, there are benefits in terms of K and S, in terms of the clay adding to the soils, and also in terms of the nutrient retention. We did find a few sites which had very high boron levels, and if that boron isn't mixed into the soil well enough, that has caused problems. It does eventually leach out of the system, but it takes a fair while. One of the key issues we did find, though, was that there was a huge range in the phosphate retention index. We've also found some clays which have a PRI of over 1,000. So when you're diluting that through the profile, normally you won't have a problem. But when they get above about 500, we're suggesting that the PRIs are high enough in the clayed soils to start binding up P and not making it available to the plants. One other small issue is that the ECs of some of these clays were quite high, 2.3 is huge, and we had white salt over the top of this clay pit. Salt is obviously highly mobile. Once you dilute it, it shouldn't be a problem. The biggest problem in using salty pits is that you've probably got a water table at 1 metre, and that's going to affect your ability to extract the clay more than the impact of the salt itself. Okay, conclusions. Yield increases of greater than 40% have been found in our long-term trials where the clay percentage has been raised between 3 to 6% within the topsoil. The effects of claying and deep ripping were additive, and deep ripping effect is short-lived, and particularly where you haven't got controlled traffic systems in. We're really suggesting that you fix the surface, line the machinery up, and then start looking at your subsoils. And 1/3 of the farmers test their clays before applying, and that was one of the key findings from a survey which we had, and we're really suggesting that farmers really need to look at their clays a little bit more before they start putting their clays in. And only a small number of clays actually had problems. So I'll leave it with the 3 key messages. The bottom one being test your clays before applying. And I'd really like to acknowledge the Liberta family for hosting the trial for 15 years. I think that's an absolutely huge effort on their part. WANFA and also GRDC and DAFWA for funding this project. Thank you.